This is lesson 3 of part 1 of the topic 1 energy for physics GCSE. So the first part in this lesson, it asks for the energy transfers for an oscillating spring. So and there's a picture shown to the side, but to understand what the energy transfers are, possibly the easiest thing to do is to just draw a couple of quick diagrams to show what happens as the spring oscillates. So we could start with the spring when it's compressed, with the object is up at the top, and sometime later the spring will be stretched, the object is moving down a certain amount of speed, and then eventually the spring will be stretched as far as it can go. The object is now not moving anymore, and then the spring will start compressing again. The object is moving upwards until eventually the spring is compressed as much as it can, and again the velocity is again 0. So this shows a full oscillation from the top, starts to move downwards, reaches the bottom, speed goes to 0, starts going back up again, so it starts moving again with a certain amount of speed until it reaches the top again. And what we can say is that when it's up at the top here, it's got gravitational potential energy. Here it's moving, it's still got some gravitational potential energy, but it's also got kinetic energy because it's moving. But here it's not moving, so it doesn't have any kinetic energy. And we can say that here, if we assume that it was just touching the ground, so it's got no gravitational potential energy, there needs to be another form of energy. Remember, energy cannot be created or destroyed. So the gravitational potential energy was being changed into kinetic energy because the object was moving. But eventually there is no kinetic energy and no gravitational potential energy. So this is where it has elastic potential energy. So we can write that in words. So I'll just put this into words. So we have the spring is fully compressed. The object has gravitational potential energy. When it's compressed, it also has some elastic potential energy. So then we say as the object moves down, the spring starts to stretch and the object moves. So there is a transfer from gravitational potential energy to kinetic energy. Eventually the spring stops stretching, so the object stops moving. The energy has been transferred to elastic potential energy. Next, we're going to look at what are the factors that elastic potential energy depends on. So we had this for gravitational potential energy and for kinetic energy. And here, elastic potential energy just depends on two things. There's something called the spring constant. So what type of spring do we have? What's it made from? How big is it? How stiff is it? So that's called the spring constant. And we have the extension. How much has the spring been stretched or compressed? So extension, although it says extension, it can mean how much the spring has been compressed as well as how much it's been stretched. So we can write that in words. We say that the elastic potential energy is equal to, it's a half multiplied by the spring constant multiplied by the extension squared. So we can write that in symbols. The symbol for the elastic potential energy, once again, very similar to gravitational potential energy. And kinetic energy, it's capital E with the small e beside it. It's measured in joules. Symbol for the spring constant, that's just simply the letter K, and that is measured in newtons per meter. And then finally we've got the symbol for extension. The symbol for extension is small e, and it's measured in meters. So we met the idea of the spring constant before when we were doing the forces topic, when we saw that the amount of force applied to a spring was equal to the spring constant times the extension. We're now using this again to say that the amount of energy that's stored in a spring is equal to half times the spring constant times the extension squared. As before, we need to be able to rearrange this equation very similar to the kinetic energy equation. So we have the elastic potential energy is a half times the spring constant times the extension squared. So to rearrange this, we need to get rid of the half, which means we need to multiply both sides by 2. And we need to get rid of the extension squared, so we need to divide both sides by the extension squared. So we get the spring constant, it equals 2 times the elastic potential energy divided by the extension squared. And likewise, when we have a question where we need to work out the extension, we need to again get rid of the half, so we multiply both sides by 2, and we need to get rid of the spring constant, so we need to divide by the spring constant. But then, as with the kinetic energy questions, we need to remember that the extension is squared, so we need to take the square root of all of that. And I've just written these out in words. Once again, we can see how useful it is to use symbols. It's much easier when we have to do rearrangements. It's also much quicker to write it rather than writing things out in words. So we have a question to do. We have a spring, has an extension of 2 meters. This is the spring constant. We're calculating the elastic potential energy. And as always, the most important thing is that we do the 4 steps. So we're going to start by writing out the numbers. I've got E is equal to 2 meters. The spring constant is equal to 12 newtons per meter. And I'm looking for the elastic potential energy. The equation, the elastic potential energy is a half times the spring constant times the extension squared. So I put in the numbers, a half times 12 times 2 squared, which gives me an answer. Once again, you must make sure that you're always using your calculator. So that gives us an answer of the elastic potential energy stored in the spring when it's been extended by 2 meters is 24 joules. Okay, so 4 more questions to try. As usual, we're always going to use the same 4 steps. So we have a spring which has a spring constant of 5 newtons per meter. It's been extended by 20 centimeters, so I can do the conversion to write that in meters. So that gives me 0.2 meters. So I divide by 100. And again, I'm looking to calculate the elastic potential energy. Step 2, write out the equation. Step 3, put the numbers in the equation. And step 4, calculate the answer. So I have 0.5 multiplied by 5 multiplied by 0.2 squared, and you need to be careful that you always only square the 0.2 when you do this calculation, which gives us an answer of 0.1 joules. Now we then have a spring with a spring constant of 50 newtons per meter. This time it's extended by 2.5 meters. And again, we're calculating elastic potential energy, which is a half times K times the extension squared. So that gives us a half times 50 times 2.5 squared to give us an answer for the elastic potential energy is 156.25. So I'm going to write that as 156 joules. I would be justified in this question, for example, as writing this as 160 joules, since I have two significant figures in the question. Next one, I've got a spring stores 1.8 joules of energy. It's been extended by 0.6 meters. And in this case, I'm trying to find what the spring constant is. So that was my step one. Step two, I write out the equation. And I'm going to do the rearrangement. So I want to get k as the subject, so I need to get rid of the half and the e squared, which means that I need to multiply both sides by 2 and divide both sides by the extension squared. So now I get, when I put my numbers in, 2 multiplied by 1.8 divided by 0.6 squared, which gives me the spring constant is equal to 2 multiplied by 1.8 divided by 0.6 squared, which gives me an answer of 10 newtons per meter. If you're not sure, if you think you might have made a mistake, very easy way to check. I can just go back. Remember, this is my equation. I think that should be 10. My extension is equal to 0.6 meters. So I can very quickly work out what that would give me. I've got a half multiplied by 10 multiplied by 0.6 squared, which gives me an answer of 1.8. So I'm confident my answer is correct. Okay, then finally we've got a spring has a spring constant of 8.0 newtons per meter. It's storing 32 joules of energy, and here we want to calculate the extension, and it's one of those questions where it says give your answer to two significant figures. So again, the equation is a half times the spring constant times the extension squared, and I'm going to rearrange this. So I've got the extension equals, which means I need to get rid of the half, so I do that by multiplying both sides by 2. I need to get rid of the spring constant term, so I divide both sides by the spring constant, and I need to get rid of the squaring, so I do that by taking the square root. So that gives me E is equal to the square root of 2 multiplied by 32 divided by 8. So it gives me an extension of 2.828427125, which is square root of 8. But again, I have to give this to two significant figures, so I write that 8 is 2.8 meters as my answer. Now, as well as having questions where they give us the numbers and we have to use our 4 steps to work out the answer, we may also be given questions where we're shown things in terms of a graph. The graph usually is shown with force on the y-axis and extension on the x-axis, and we've got the equation from our forces topic. Force is equal to the spring constant times the extension. What that means is that force is directly proportional to the extension. So whenever we have something that is directly proportional, we show that on the graph by drawing a straight line going through the origin. So put down my ruler and I'm going to draw a straight line going through the origin like that. So that's the graph that we would expect to see for a spring. Now, one thing we can notice is that by dropping a line down here, what I have is a triangle, and the area of a triangle is equal to the half times the base times the height. That's what we learn from maths. So in this case, what we've got is the area is equal to half times whatever the extension was multiplied by whatever the force is. Okay. But we already know that the force is equal to K times the extension. So that means the area, this area under the graph, it's equal to a half multiplied by the extension. Instead of putting F in here, I'll put K times E. So that gives me the area is equal to a half KE squared. We've already seen this. This is what we defined elastic potential energy. So the energy stored in a spring can also be calculated from the area under a graph of force against extension. Remember, the elastic potential energy is equal to half times the spring constant times the extension squared. So this area under the graph is equal to the elastic potential energy. So you might be given a question where they show you the graph and you have to say count the squares underneath the graph or use the numbers on the axes to work out the area, which will tell you what the elastic potential energy is. Okay, finally we have this question which says a force of 15 newtons applied to a spring with a spring constant of 60 newtons per meter. Calculate the elastic potential energy. So step one, we have the force is 15 newtons. We've got a value for K, which is 60 newtons per meter. We want to calculate the elastic potential energy, but problem, we don't know what the extension is. This would typically be a 4 or 5 mark question because here we're going to have to use two equations. So I'm going to do this in two parts. So on this side, I have force equal to 15 newtons, spring constant is 60 newtons per meter. I'm missing the value for the extension to be able to work out my elastic potential energy. So I'm going to work out what that is first of all. So I've got force is equal to the spring constant times the extension. So that gives me, rearranging that, the extension is equal to the force divided by spring constant. So the extension is equal to, putting in the numbers, 15 newtons divided by 60 newtons per meter to give me a value for the extension of 0.25 meters. So now I can now work out my value for the elastic potential energy because now I've got a value for K, I've got a value for E, I'm looking for the value for this. My equation, as before, is the elastic potential energy is equal to half times K times the extension squared. So putting in the numbers, that gives me a half multiplied by 60 multiplied by 0.25 squared. And that gives me an answer of, putting it into the calculator, 0.5 times 60 times, and remember, make sure you only square the 0.25. And that gives me an answer of 1.875 joules. But I'm going to write that to two significant figures as everything else has been, so 1.9 joules as my answer. And that's the end of the first part of the topic 1, energy.